Okay, I'll talk a little bit about what makes ScyllaDB such a great database and how we're working hard to make it even better in the future. So we'll talk about the first ScyllaDB commitments, which are basically the core values of the database and the company behind it, what we're trying to achieve. And second, we'll present the ScyllaDB roadmap, which is where we're going with this. So let's start. So the first two are pretty simple. High throughput and low latency. It's what we are famous for, being 10 times faster than Cassandra while maintaining really low latency. And we've seen that with the Outbrain presentations and the Kenshu presentations. And we'll talk a little bit about that. Compatibility with the Apache Cassandra ecosystem, the huge body of work that already exists that's compatible with Cassandra, drivers, add-on, layered-on databases, and all of that. And workload conditioning, which is not really new, but it is a new term, an umbrella term for several features that we are adding to ScyllaDB over time. All right, so let's talk about throughput and latency. And what we have here, let's see if my aim is good. OK, so this is a graph that's taken from one of our bug reports. And maybe if you find the actual bug report with that, and maybe Alec will give you one of the leftover prizes. So let's see what happens here. So here we have the cache operations in the database. And this is a simple load running on a developer's laptop. So it's only about 10,000 operations per second. And you can see that the cache hits start low and climb, and the cache misses start high and then drop down as the cache gets warmed up. The graphs look like mirror images of each other. And this is because this is a fixed load. So we're running at a fixed 10,000 operations per second. We're not pushing the database as hard as it can be. So any operation that's a hit is taken from the misses. So their sum is a fixed line, and they're mirror images of each other. You can see in the graph in the center right, you can see the effect on memory. So LSA memory, that's the memory that's used by the cache. It starts low, and then it gets filled up as the cache hits increase. When the slope is high at first, because at first the miss rate is high, so we're filling up the cache quickly. Later, it sort of levels off. And let's see the effect on how the cache internally works. So in green, we have cache insertions. So this is the case where we have a piece of data that did not exist in the cache, a cache miss, and gets inserted into the cache. And in the light blue, what we have here is evictions. And this is a case where we're taking a piece of data out of the cache. We're looking at the tail end of the LRU, and we're throwing away some memory to make room for the others. So you see that it starts, while we fill up memory, we have plenty of memory. We're just filling it up rapidly. And at one point, memory gets filled up. We only have half a gig in this workload. Then we have a spike where Scylla starts throwing away memory out of the cache as fast as it can in order to make room for new data, hot data. And here below, you can see the impact on Cassandra stress. So this instrumentation is talking to Cassandra stress, not to Scylla. And you can see that the average latency and the 99% latency are rising a little bit. But we also have spikes when we have these evictions happening. And this allows us to understand performance within Scylla and debug it and make sure that the latency for you is not as bad as we see it, so we can improve things for you. And also, these measurements are also available to Scylla itself. So Scylla can use these measurements and feed them back to the database engine in order to tune itself on the fly. And by the way, there will be a presentation later on by two of our engineers, Glauber and Tomek, who will show these metrics and many, many more. There is a huge wealth of metrics, hundreds, that you can use to understand how Scylla works and what it's doing. All right, so the effects of when we have metrics like in the previous graph, we can use them to improve the database. So so that we can get this graph, and this is the production benchmark load, the YCSB load. I think that many of you have seen it in our blogs already, and it shows how Scylla can deliver much better throughput on a much smaller cluster while delivering much lower latency. So this is a YCSB load running 50% mixed reads and 50% mixed writes. We have a 3-node Scylla cluster competing against a 3-node Cassandra cluster, a 9-node Cassandra cluster, and a 15-node Cassandra cluster. In all cases, the throughput is much better, and for many loads, even more important, the latency is much lower. So what's the good thing about throughput and latency? So of course, more is better, but it also translates into money. So it reduces your capital expenses if you're running your own data center, or your cloud expenses if you're fans of Jeff Bezos. It reduces the need to manage large clusters, and operations are a big component of your costs. You need to have people monitor the clusters, fix any issues. It reduces the support costs. So if you need an enterprise license, then having fewer nodes means that you're paying less, and it reduces the failure rate. The more nodes you have, the more failures you can expect, and those failures are pretty bad. Not just for your application, even though the cluster is fault tolerant, there is still some impact, and also someone has to go and fix them. So it's not just equipment. If you have, you don't have so many emergencies, so you don't have to page someone in the middle of the night to fix something. And while a node is out due to a hardware failure or a software failure, you run the risk of having a double failure. So if while you're fixing up that node, you have a second node go down, then you're below your quorum. You cannot achieve quorum, and your requests start bouncing off with errors. And that starts impacting your application. So the fewer nodes you have, the fewer the odds of having this double failure occur for you. There are some studies that Google have shown, and also Amazon, that when you have high latencies, then a web user will stop using your website and will move off to competitors. So having lower latencies means that you can serve your web pages faster, and often those web pages include requests. Many different requests from the database are used to build the web page. So having a consistent low latency is really critical for that. And in the ad tech business, there's auctions for the privilege of serving an ad for you. And when they win more of those auctions, then they can serve more ads and make more money. All right, so that's performance and latency. Let's talk a little bit about compatibility. So we've seen below in the previous presentations that compatibility is an important win. There's a huge ecosystem of add-on databases and services on top of that, but also the simple things like the drivers. It's really great to have someone say, I started ScyllaDB and connected with the Go driver, and everything just worked, or with the PHP driver or the Python driver or whatever. Everything just works because of the compatibility. So the point is that you can reuse your existing investment and knowledge, and also the ecosystem's investment and knowledge. If there's a body of code that works with Cassandra, it will work with Scylla, and you can cut time to market, cut the development time. Everything will work faster for you. And the third item that I mentioned is workload conditioning. So workload conditioning is a way to use feedback loops. You measure something internally from the database, and you use that to change how the database reacts. So this is a diagram of how ScyllaDB works, a very high-level diagram. So you have on the left, you have the various internal processes like commit log writer, the memtable writer, the compaction manager, and the query, which is serving the reads, and repair, which is for maintenance operations. And on the right, we have the various hardware resources that are connected. Maybe a WAN is not really a hardware resource, but we have the WAN, the network, we have the storage, and we have the CPU. And in the middle, we have the C-star scheduler. Now, why do we need a scheduler between them? If you look at a regular database implementation, a common open source database implementation, when it needs to do a write, it just issues a write command and waits for that to return. The problem is that it only works if you're severely underutilizing your hardware. And at ScyllaDB, we want to maximize utilization of the hardware. If you're running the hardware at 100%, and we've seen ScyllaDB nodes run with 3 gigabytes per second of read and 1 gigabyte per second of write. If you're running at those levels of performance, if you just throw things on the disk and wait for them to return, those internal processes will compete with each other, and there is no way to predict which one will win. So you might see compaction dominating your load, and your reads start to suffer, or maybe you have the commit log and name table dominate the load, and then compaction falls behind, and then your reads begin to suffer because they have lots of SS tables. So what we do is have a feedback loop, and we have the C* scheduler make a selection between the various internal processes and decide what priority each process gets to use, how many shares of the SSD it gets to use, and we can adjust them on the fly and without user involvement to deliver the correct response. So let's look at a couple of examples. First, we have the compaction backlog manager. So it measures the backlog that we have for compaction, how many SS tables are awaiting compaction. And it uses that to adjust the priority that compaction gets from the IO scheduler. So the way that works, if the backlog starts getting higher, which means that reads are becoming slower, and also that we will have a lot of work to do later, instead of queuing up all of that work, it increases the shares of the compaction process, and compaction starts becoming faster. Reads and writes are getting a little pushback, and because of that, future reads will be faster. And on the other hand, if we see that compaction is actually making good progress, perhaps too good progress, we tell it to lay off a little bit and pull back and not write so hard. And this makes room for your reads and for your writes to arrive. So this way, all of the components in the system dynamically adjust themselves to deliver a good response. Let's look at another example. And we have the memtable writer. And as we write, the memory gets full with dirty memory. And there is a memtable writer process that flushes the memtable to the disk, creating a new SS table. And that also has some rate at which it is writing. If it is writing too slow, then what happens is that the memory will fill up, and we will not be able to accept new writes until that memtable is converted to an SS table. And conversely, if it's written too slowly, then we are actually using disk bandwidth for writes, which we could have used for reads. So what we try to do is select the correct writing rate so that memtables will be converted to SS tables at exactly the right pace. Too fast, and you're just using up disk bandwidth. Too slow, and your memory is filling up, and you cannot accept new writes. So these are just 2 examples, and we have many more. Here are some. Not all of them are already present in Scylla 1.3. Some are queued for 1.4, and some will be added later. But they're all examples of how we are working very hard to condition your workload, to make sure that no matter what you throw at Scylla, it will tune itself in order to provide the best response. It will, if you're underutilizing your hardware, everything is good. Everything gets direct access to the hardware. But as soon as you're beginning to max out your resources, and they can be the network, they can be the disk, and they can be the CPU, then the C* scheduler will arbitrate between those internal processes to make sure that no one gets left behind. So let's look at some examples. Maybe the #1 complaint you see on the Cassandra mailing list is about compactions being piled up, and then you have to increase your compaction bandwidth, and you have to keep changing that because your loads change. And once they start piling up, then your reads become slower. So this is fixed by having compaction backlog monitored and used as feedback. We also ensure that repair makes forward progress. So you're adding a new node, or maybe you're doing a cross-one repair. The IO scheduler allows it to ensure that the repair process gets enough bandwidth to read in the data from both sides, compare them, and send the right amount of data. And instead of being overwhelmed by reads and writes, or perhaps vice versa, perhaps repair might use too much bandwidth and cause your regular read and write load to fall behind. We've seen how memtable memory, we can prevent it from being filled up by tracking the amount of memory that's in use and using that as feedback for the IO scheduler. We isolate read loads from write loads. So we've seen that on many customer loads where everything works well when you're doing reads, but you start doing writes, and suddenly the read latency starts shooting up, and the IO scheduler allows us to isolate it. Something we've also seen is a problem with cold nodes. So you're doing an upgrade, you're rolling upgrade, or perhaps you're recovering from a failure, or you're commissioning a new node. So that new node starts, and its cache is completely cold. When it's asked for reads, it will start hitting the disk for 100% of those reads. And if your disk isn't very fast, then that's going to show. So what we are going to do is keep a measure of the heat map of the various nodes. So we will assign, say, a virtual temperature to each node. And if the cache is warm, then all of the nodes will know that. If the cache is cold because the node just started up, the nodes will know that as well. And they will transmit to each node, to each replica, a proportion of the load that is designed so that it will not be overwhelmed on one hand, but also allow it to warm up its cache on the other hand. And these are, again, they're just examples, and we have many more instances of these workload conditioning items. All right, so let's recap. We have performance and latency that work to reduce your cost, your equipment acquisition cost, your cloud cost, and also your operational costs. We have the ecosystem compatibility, which allows you to select from a large body of drivers and add-on software like graph databases or query engines that work with Scylla. And we have workload conditioning, which really simplifies your operations. It allows you to change your workload without thinking about retuning everything. You just throw your load at it, and Scylla takes it up. All right, let's look at the roadmap for the coming releases. So for the near term, we're working hard to bridge the gap with Cassandra. So materialized views and secondary indexes, we're working on them. The reason that I'm stating them as one item is because we're implementing secondary indexes in terms of materialized views. For us, it's good because it's less work. We implement one feature and get two. And for you, it's good because in this kind of implementation, secondary indexes will scale with your cluster size. So as you increase nodes, secondary index performance increases with the cluster size compared to the regular secondary index implementation, which does not scale. We will also add counters, lightweight transactions, a management stack. So we're dividing that into two phases. The first phase will be a simplified stack. You've already seen some of the monitoring. We will also add operations. We will introduce formal support for the REST API. I will talk a little about that in another slide. And the container orchestration integration used for Docker and containers. Why is that so important, and why is that so difficult? The whole world seems like it is moving to Docker. Everyone is deploying containers, and we've seen that in Henrik's presentation a few presentations ago. And why is it so difficult? So when you start up a Scylla node, what it does, it completely takes over your hardware. So if you have 128 gigs of memory, Scylla will use about 120 of those. And if you have 48 logical processors, then Scylla will use all of them because it really likes to max out your hardware. But in a container environment, that's a shared setting, and you're likely to have multiple processes on that machine. So we've added support for Scylla to be a little friendlier towards other processes running on the machine, give up some of the memory, do less aggressive polling, and not bind itself to the CPUs. So you give up some of the performance, but you can collocate Scylla containers with other containers. Of course, if you dedicate a machine to Scylla, then you get the full performance, and you can still use Docker and the orchestration solutions, such as Mesos or Kubernetes. And a lot of that is already present in 1.3, but we are working to improve that for the next releases. So I mentioned the REST API. Why have another API for management? Right now, the standard way to manage Scylla is using JMX, and if you're not using JMX directly, you use a no tool command. But the problem is that these tools are pretty slow, and they're fairly clumsy. It's hard to do programmatic management from non-Java applications, and even in Java, it's a little bit clumsy. So we're moving to the standard, which is a REST API. You already have a REST API, but it doesn't have formal support, so it's not completely documented, and it might change a little bit. So in the coming releases, we'll need to introduce formal support for the REST API. All right, so for the medium-long term, we will introduce a new storage format and multi-tenancy. I will not talk about them now because I have some slides coming up. And we will also introduce support for analytics. You already saw that you can do analytics pretty easily with Presto and Spark, but it is still a little bit clumsy. You need to set up a new cluster, and you need to provision it. You need hardware for that. And so we will introduce built-in support for analytics, that is full scan queries inside Scylla. And these queries will be able to take advantage of all of Scylla's performance advantages. And so you will get very fast analytic queries. We will also introduce the full text search and additional protocol support. And by that, I mean protocols like Redis, so that we can leverage all of the hard work we did on high availability, fault tolerance, and on performance, and just bolt on a new protocol processor, and you can use your Redis applications with Scylla, or perhaps other databases as well. And again, other features that we will add is a file system bypass. You might be familiar with our TCP stack using DPDK to bypass the kernel to deliver extra performance. We will do something similar for the file system and have direct access from Scylla to the disk that improves performance, reduces latency further, and allows us even more control over all the IOs that we push to the disk, so that we can do even more of the workload conditioning that I talked about earlier. Again, on the low-level front is NVDIM and 3D Crosspoint. How many people are familiar with those terms? Can I see some hands? So hard to see with a glare, but I guess that's maybe 20%. So NVDIMs are a new class of memory, somewhere below RAM and above SSD. So if you look at the traditional memory hierarchy, with the caches that are small and fast and close to the CPU, and beneath them the RAM, which is larger and is a little bit slower, but cheaper. And below that you have SSD storage, which is cheaper than RAM but a lot slower. So NVDIMs, or 3D Xpoint, which is the Intel term for them, is a technology that gives you larger amounts of memory than DRAM, but less memory than an SSD, which is also faster than SSD but slower than DRAM, and at the corresponding price point. So you might see a server with 128 gigs of RAM and maybe a terabyte of non-volatile DIMM memory, and maybe 10 terabytes of SSD. And this way, you can increase the performance by moving hot data and the commit log data onto this non-volatile memory, which, since it's non-volatile, it can survive failures. And this way, you can improve the system much more, sort of like hierarchical storage. All right, let's talk a bit about the file system format and why we're introducing a new one. So the current format we support is the same as the one supported by Cassandra 2.1. And one of the problems with it is that it is very metadata intensive. So a lot of the metadata, like the column names, are replicated all over the disk, and that causes a lot of bloat, and it slows down read and write times. Now, the 3.x format in Cassandra fixes some of the problems, but not all of them. There are still issues with large partition support, and we would like to have our large partition support be first class, so you don't pay a penalty for having large partitions. We've started that with Scylla 1.3, and we're working to improve that. And as part of that, we will have a new storage format, which will be very dense. So it will not bloat your disk usage. It will be very fast, and it will give good support for large partitions. Multitenancy. Now, that's a feature we are very excited about. We've seen, and I think that in some of the presentations before, we've seen that a lot of organizations have several Cassandra clusters. They might not be so large, but there are many of them. And if you consider that even a small cluster might have 9 nodes, because you need 3 nodes for a replication, and you might want to run them in 3 different data centers, then even a small cluster is quite large. Now, that has a lot of problems. First of all, your hardware is going to be underutilized. So for every application, you're going to have a dedicated cluster, then you're going to be buying a lot of hardware or paying for a lot of instances on Amazon. And it also duplicates a lot of operations effort. So if you're doing an upgrade, or if you're doing backups, or if you're working with, if you're fixing problems, then you're duplicating that effort over many, many clusters, and you don't want to do that. So what we're introducing with multi-tenancy is the ability to have a single large virtual physical cluster, and you can provision multiple virtual clusters from that physical cluster. In the same way that if you have a large physical host and you provision multiple virtual machines out of it, which are independent, but they are sharing the resources, and in the same way that you can use Docker to slice a physical host into multiple virtual hosts, not virtual machines, but multiple containers, you can do the same with Scylla multi-tenancy. And this will allow you to have one cluster that your ops team maintains. It can be a fairly large cluster. And when you have a new application that wants to use Scylla, you just issue a single command to create a virtual cluster. And you get a new cluster that behaves exactly like a regular Scylla cluster. It has its own IP addresses. It has its own users. It has its own key spaces. Everything you can configure in a physical Scylla cluster, you can configure in a virtual Scylla cluster, but it only gets a portion of the resources available in the cluster, and you can configure that. So you can say that you want to assign this virtual cluster maybe 5% of the memory and the CPU resources and 10% of the storage, and it will not be able to affect the performance of other virtual clusters running on the same physical cluster. So you get workload isolation, and when that application grows, maybe it's a big hit and your users like it, you can simply increase the amount of resources you provision for it, and suddenly it becomes faster and can store more data. And now when you do operations, you do them only on the physical cluster. So if you need to add nodes, you add nodes to that physical cluster, and all of the virtual clusters that share that physical cluster enjoy the benefits. And of course, you provide SLAs. You specify for each type of resource how much each virtual cluster gets. All right, so to recap, we were working on bridging the gap with the Cassandra, providing all of the features that your applications use. We were working on our own ScyllaDB features, which are independent from Cassandra features, and we're also adding meta features, such as multi-tenancy, that allow you to utilize your Scylla clusters better.